Good morning, everyone. Let's start the class now. It is already late. I was waiting. Today's topic is we have to study today a magnetic and dipole moment. We have to study two things today. One is magnetic dipole moment, and another is torque experienced by a magnetic dipole or a current carrying loop in a uniform magnetic force. So the first topic is magnetic dipole moment. Then we will study about torque, torque experienced by a current carrying loop in a uniform magnetic field. In a uniform magnetic field. Okay, now everyone seems to have joined now. So let's begin with magnetic dipole moment. In electrostat, you might have studied electric dipole that consists of a pair of the charges of a pair of two charges of opposite nature and same magnitude. Similarly, in magnetism, in the case of a bar magnet, you have south pole, or we can write here. In the case of a bar magnet, you have a north pole and a south pole, and if it is dipole, magnetic pole, pole strength is m, and the separation is say L. Then magnetic dipole moment is m pole strength times distance of separation. But what about the magnetic dipole moment in the case of current carrying in a loop? We have to study that one. In the paramagnet, it was pole strength times distance of separation between the two poles, the north pole and the south pole. And we know a loop, a current carrying in a loop, also produces a magnetic field. Just like a magnet, a current carrying in a loop has also a magnetic field around it. And how do we calculate the direction of magnetic field? Using right hand, we calculate the direction of the magnetic field. Yeah, say if the current is I, and you have a loop here, so it may be a circular loop, or it may be a square loop, it may be a triangular loop, any loop of any shape, but it's carry some current. Then the loop behaves, as a magnet because it produces magnetic field. So how to calculate magnetic dipole moment in case of current carrying loop? So that we have to study here. And you might have studied in lower classes that magnetic field lines start from North Pole and end at the South Pole. This is the direction. This is how you use to draw magnetic field lines in lower classes. And inside the magnet, it is like this. It is a closed loop. And now let's talk about a magnetic dipole moment. A magnetic dipole moment I said in the case of a bar magnet, you write in a magnetic in a dipole moment as as pole strength times distance of separation. But in the case of a loop, a current carrying in a loop also behaves as a magnet because it produces a magnetic field. Eh, If we find out the direction of magnetic field here, see the field is in a inward. Magnetic field is perpendicular to the screen and it is inward. So FD current carrying in a loop has a magnetic magnetic field, and let's see how to calculate the magnetic and dipole moment. In the case of current carrying, let's clear these things. Current carrying in a loop, the magnetic and a dipole moment is calculated as we can write in a NIA here. So what are these terms? N is the number of turns. If it is only one turn like this one, then you just write in I into A, current times area, number of turns, then and I is current in the loop, and A is area of the loop. This is fine, and this is how we can calculate the magnitude of the magnetic dipole moment. In case of a magnet, in case of a bar magnet, suppose this is South Pole, this is North Pole, then a magnetic dipole moment was calculated. Its pole strength is taken as minus m, and this it's in a plus m, and magnetic dipole moment was pole strength of any one pole times distance of separation. That is the length of the paramagnet. And here we have this relation, area of the loop. And what about the direction of magnetic dipole moment? Here it is in a S2n. This was the direction of magnetic dipole moment in a South Pole to North Pole in case of a bar magnet. But what about this current carrying in a loops? So let's save this one. Let's clear this one. And let's draw a few loops. It is a circular loop, it carries current. I said, and it may be a square, it may be rectangular, it may be a square. This is a rectangular. Current may be clockwise or anti-clockwise. Or it may be a square, all sides are the same here, equal in length. Now we have to find the magnetic moment. The magnitude will be how much if the current is I and its radius is R, then you have here N I into pi r square and IA. Here, but N is the number of turns. If you have only one turn, then you just that pi r square I. Here you have if this side is A, this side is B, then you have N I A into B is the area, and here you have magnetic moment. N is the number of turn, and I A square is the area of the square. This is the magnitude, but what about the direction? In order to find the direction, direction of M, direction of M, what we do, called the four fingers, of right hand, except thumb, in direction of a long current or in direction of current, then thumb will point in direction of magnetic dipole moment, and it and also a magnetic field. So here you can say what is the direction of a magnetic moment here, inward or outward. You can call the fingers of right, call the four fingers of right hand in the direction of the current, then a thumb will give the direction of magnetic moment, and see it is perpendicular to the screen and inward. So here also you have a magnetic moment inward. Here also you have let's change the direction here. Let's change the direction of current. Then you have suppose you have anti-clockwise. Then magnetic moment here will be you can call the fingers of right hand along the direction of current, and then you see your magnetic moment here is perpendicular to the screen and outward here, perpendicular to the screen and inward. This is how we calculate the magnetic the direction of magnetic moment. One graphical representation is this, say if the current is this clockwise, we draw yes, like this. If we draw yes and put the arrow, this means what? The clockwise, we are looking at the loop from the outside. The loop is on the screen, and we are looking from top view. Then our current is now anti-clockwise. This means what? Outside, the outer part of this loop behaves as south pole. This outer part behaves as south pole, and inner part is north pole. That's why the magnetic moment here is inward. Is inward. We just put in a cross for inward. So this is also one representation for north pole. You can just draw an little bit in a bent one. Suppose now your current is anti-clockwise, and this means outside the loop, outer part of the loop means top side of the loop behaves as the north pole, and the other side will be south pole. So the direction is what? Yes, 2n, and means from inner side to the outer side. And if we use right hand to find the direction, Then also we can find the direction is what, outside, perpendicular to the plane of the screen, and outward. Simple is using a right-hand rule. This is very simple. Its direction is clear. So for the loop, magnetic moment is how much? It is N-IA, where N is the number of turn, I is the current in the loop, A is the area of the loop. And direction, we can find the direction using right hand, just like we used to find the direction of magnetic field, due to current carrying in a circular loop. Is it clear? Is it clear how to find the I said, we can calculate, magnetic, moment, magnetic, moment, due to a current carrying, you already know, you studied, magnetic field due to a current carrying, coil, that a current carrying, coil or a current carrying in a conductor, produces magnetic field around it. Oh, so our loop also, this current carrying in a loop also produces a magnetic field around it, means it behaves as a magnet. And the direction of magnetic field due to each loop here, we can find the direction, we already studied that. And how do we express the magnetic moment then? In case of a bar magnet, we used to calculate dipole moment, as if it is south pole, this is north pole. Its polar strength is written as minus m, and this polar strength of north pole as plus m. Then, and if it is the length of the magnet or separation of the poles is L, then the magnetic moment is written as m into L. Polar strength of any one of the poles, as the magnitude of polar strength is same for both poles, only nature is different. And the direction was of the magnetic moment was from the south pole to north pole. In case of a paramagnet, in electrostat, used to calculate the magnetic moment as if this is a minus and this is in a positive charge of same magnitude, but opposite in nature, and the separation separated by some distance L, then electric dipole was written as magnitude of charge of any one of the charge, as both have same magnitude, into distance of separation, and direction was negative charge to positive charge. But in case of a current carrying, in case of a current carrying loop, the magnetic moment, is expressed as current in the loop times area. And if you have only one turn, then it is fine. If you have more than n turns, then we write n times current into area. This is how we write magnetic moment due to a current carrying loop. And regarding direction, in case of a bar magnet, we said the direction is from south pole to north pole. In an electric dipole, we said from negative charge to positive charge. Here, in case of current carrying loop, the direction is calculated by right hand rule. We curl the 4 fingers of right hand along the direction of the current, along the direction of the current, and the thumb will give the direction of magnetic moment. This is the simplest way to find out the magnetic moment. And just let's just stop this one. Okay, fine. And here in paramagnetic, you have from South Pole to North Pole, and a South Pole to and a North Pole, and a means minus m to m direction of magnetic moment. And see here, magnetic moment is in a pointing in. And what is the direction of thumb here? If we call the four fingers of right hand along current, then what will be the direction of thumb? Elena, thumb is pointing inward. So the direction of magnetic moment is inward. Yes, inward. Magnetic moment, direction of any magnetic moment is inward. So towards the inner side, see, in a biomagnetic, you have direction of magnetic moment as from south pole to north pole. South pole to north pole, yes to n, yes to n. This one is minus m, polar strength, this is m. And this was the direction of magnetic moment. And here, the direction of magnetic moment, as found by right hand curl rule, is inward, perpendicular to the screen of loop and inward. This means your inner, towards the inner side is your north pole of your loop, and towards the outer inner side is here in a south pole. This is a for simplicity. This is graphically represented like this. If you have a current anti-clockwise, and if you write yes here and put arrow, then see arrow. The arrows are have in same directions. This means if you have anti-clockwise current, then this means outer side is the south pole. Or we can simply find out by the right hand rule. We call four fingers along current. Then thumb will give the direction of magnetic moment, and thumb is pointing inward hairs. Thumb is pointing inward, and see the direction of magnetic moment in the case of bar magnet. South to north pole. Magnetic moment is towards north pole from south pole. Means here, as the magnetic moment has direction perpendicular to the plane and inward, means your inner side has a north pole and outer side has south pole. Is it clear, Elena? Is it clear how to find the direction? Yeah. Let's save this one. And let's clear. Now let's note a few more points. Let's write some additional points. Suppose we have we have a rectangular loop here, and it is A, B, C, and D. And suppose your current is anti-clockwise. This is the current. And the magnitude of magnetic moment is how much? NIA. Area is also taken as a vector quantity. When you write this in vector form, then we can write this one as Ni, number of turns, just a value. Current is a scalar quantity here. We can take area as the vector. Then how to calculate the area vector? So how to calculate this area vector, calculation of area vector? You might have studied and vectors, we can keep the scalar quantity as it is and write area vector, if we have to calculate the area vector of this loop, then see the direction of arrow, we have to calculate the area in the same order, in which we have the direction of current here. So the current is is in a clockwise. So area, you can write AB vector into BC vector, AB vector into BC vector cross BC vector, AB cross B. This is also one way. Or you can write BC cross CD. That is also correct. And BC vector cross CD vector. That is also correct. But we can't write in reverse order. I mean, you can't write CB cross BA. We have to write in the same order in which we have the direction of the current. Means either you can write this one, or you can write NI and BC cross CD, or we can write NI CD vector, CD vector cross DA vector. Is it clear? This is how we calculate area vector here. And sometimes you may have coordinates of these points, a coordinate system, X, Y, Z axes are given, and when you have coordinates of these points, coordinates of A, B, C, D given A, B, C, D, and D, then we can simply write this as magnetic moment as, or means in this situation, suppose if you have coordinates of all these points A, B, C, D, coordinates are given, then how can we express AB vector? AB vector will be just this A, and here you have B, and suppose its coordinates are XA, YB. No. You can write X A, Y A, Z A, and here you have XB, coordinate of B, YB. You might have some values, ZB. Then AB vector, AB vector is written as how much? XB minus XA, and along the x-axis we have unit vector I. Similarly, you write YV minus YA, and the unit vector along y-axis is J. Similarly, you write ZB minus ZA, and unit vector along z-axis is K. Means when you have the coordinates of the 4 points, then you can represent each of the vector, A, B, C, D, A, B, B, C, C, D, D, like this. Okay, this might be clear. It is very simple. So can I proceed forward? Okay, let's solve a problem, a small question for practice, and then we'll move to torque. So I think I saved this one. So let's clear this one. Then let's try a question. You have axis given. Okay. Suppose this is your z-axis. This one is our x-axis, and this one is our y-axis, and this is the origin. And we have a loop here. We have a loop here. In which plane is this loop? In which plane? XY, YZ, ZX. In which plane is the loop? You can imagine. This side is A, this side is B, this side is C, and you have a current here. You have a current here, I. So O A B, O A B C O is a square root. It is a square, a square of side length L. Each side has the same, same side length in L. And we have to find the magnetic moment. It carries current I, side length is given L, and it is a square. If it is a square, the area will be just L square. And nothing is mentioned about, about the nothing is mentioned here. Current is given I, side length is L. And nothing is mentioned about number of turns. So we can assume a number of turns is 1. And then we have to find the magnetic moment here. And one thing more, and this angle is given, and this angle is given 60 degree. And we have to calculate a magnetic moment. So magnetic moment is affected quantity we need in both magnitude and direction. So it is it might be better to express this in vector form. Axes are given, so you can take unit vectors, unit vector. Here you have j cap, here you have I cap along positive x-axis, and here you have k cap. So you can find magnetic moment in vector form is using ijk. So if you write, you can try yourself, and I'm also doing, let's try. Okay, magnetic moment here, we can take any of the two sides, for the calculation of the area. So current is I, and area factor will be, we can take in a BC cross in a CO, or we can take in a AB cross BC. The only thing is we have to take in the same order in which we have direction of current. So let's take BC vector cross CO vector. So let's express here how much is in a BC vector real. See, BC vector is anti-parallel to your z-axis. So we can write how much its length is L. That's fine, but see the direction of BC vector. It is opposite to the direction of let's say this one, and we'll have to take another session as we have less than 1 minute. Just I'm starting another session.